Brilliant, that was prompt. Excellent, so thanks very much Stefan and Jon for setting the scene before coffee. We are now going to just take that baseline data from 2022 and we're now going to talk about what happens when you change your land management or land use in a parcel, which then tees up for that next conversation from Emily on what are the consequences on hydrology. So back to Jon now to explain our NEIRF 2 funded project on predicting soil carbon change.
Okay, so where have we got to? We've got all these fantastic context-specific data on soil carbon. So all from the same landscape, from the same soil types. And we want to understand variation in that, and we want to use that existing variation as a way of predicting, if you change the management in this field, where might you get to? And again, the scope of what we're talking about is land use change within cultivated systems. So we're looking at arable, improved pasture, and a bit later we're talking about floodplain meadows. Over coffee I was talking about trees and shrubs and forestry. Obviously that's a whole other area. And I kind of think of this as a ratchet. So if you stay within an annually cultivated system, there's so much you can do with regenerative approaches, reduced till cover crops, organic inputs to improve your soil carbon. But if you want to go to the next level, ratchet up, you need to have a permanent cover, permanent pasture, grassland, and then there's certain things you can do within that, grazing management, water management to improve your soil carbon. But then if you want to go to the next level, you need a woody cover, you need shrubs, you need hedgerows, you need trees, and then of course you're into that whole above ground carbon storage, which we haven't touched on and we're not touching on much today. So the scope of what we're talking about, and certainly before lunch, is within that arable, grassland, pasture, land use system, and understanding how things potentially could be improved within that system based on the range of data we have. So here's another of those box plots, and it's a representation of those baseline data. This time it's on an enterprise or a farm scale. So each of those letters along the bottom is an anonymised farm where we did the sampling, and again the green is the grass and the orange is the arable, so you see a big difference between those two. And we've represented it as the soil carbon to clay ratio. So again, it's our index that Stefan was talking about as an indication of the condition of that soil given the texture that you've got. And we put the lines on here, or Kathy has put the lines on here on this graph. So if you're above this line, you're in really good condition. If you're below this line, you're in degraded. So you see the vast majority of the fields are kind of in this moderate to good zone, and the grassland fields tend to be in the very good. But the really valuable thing of these data are the ranges. So you can see within a given field, there's a massive range, both within the arable and within the grassland. And that raises loads of questions. What's happening differently in these fields up here compared to those fields, these fields compared to those fields? So we see big differences between farms, between management systems, between enterprises. So there's kind of farm scale differences that we can explore, and there's also field scale within farm differences. And again, I was talking over coffee about some of the things that might explain that. There might be subtle differences in topography and soil depth that we haven't captured in our data. But what we're really interested in is those management changes that we can target to improve things. But again, it's the ranges of soil carbon data that we've got that gives us the real power, and is really the fuel for the project that we're talking about this afternoon. And so this is this is a representation of all of our soil samples, but coloured by the soil carbon percentage. So again, going from 1 up to 9 to 11. So the darker the colour, the more carbon there is there. And again, you see that the dark ones aren't necessarily clustered; they're dispersed across the whole cluster, which suggests that there's some management differences, some management explanations that we can explore. But the real, and this is a key slide for understanding our methodology and what we did in the project we're talking about today. Because we exploited that range in our data. The real value of the data is the number of fields that we've measured. So we can look for the best fields in the cluster on a given soil type. So for Elmton, where are the best performing fields in arable and in grassland? Let's identify those, and we define the best performing fields based on this soil clay, carbon to clay ratio condition. So there, if you like, that's our target, that's our potential that we could realistically achieve. We know they're in the same environment, the same climate, and there's a field over there that's doing, it's got 3 or 4% more carbon than this field over here in the same field, on the same land use and the same soil type. So that we've used that as our quantifying our headroom. So instead of modelling potential soil carbon uplift from soil principles from first principles using models or using literature, we've used this empirical data set of a way of estimating our headroom, just exploring the range within our data. So you could call that space for time substitution. We're saying, well, we know that this field has got higher carbon, so if we change our land use, potentially we could get to it. And that's what we did in this analysis. So again, these are the farms along here, and then this is the potential soil carbon uplift if we went from an arable field to a permanent pasture. So we take each of those arable fields and then we say, for that soil type, what are the best performing grassland fields based on the carbon to clay ratio? And let's look at how much carbon we would get to if we had an equivalent management to those fields. So this is this is our starting point for our arable fields, and then this is the potential extra carbon you could get if you went to that best performing grassland field. So these numbers I think are quite big. Remember we're in the top 30 centimetres, so sometimes you see carbon uplift reported just for the surface layer. This is the top 30, so they're a bit bigger. But based on our work at Rothamsted on long-term experiments, where we've got experiments comparing arable and grassland and herbal layers and arable reversion, they're realistic. So we're talking about a difference between 50 and 100 tonnes per hectare. So in the top 30 centimetres in arable fields, we're around an average of 80 tonnes per hectare. It's all organic carbon. In grassland fields, we might be up to 130, 140. So that's the kind of uplift we're talking about. But again, the interesting thing is the variation. So within a given field, depending what your starting point is, your starting arable field, the potential for uplift is very, very variable. So we need to be looking at this on a field by field basis, understanding the starting conditions, understanding the environmental context, the texture of those fields, and then the potential for sequestering more carbon, capturing more carbon. Is that kind of clear? Is that okay for now? I'm seeing lots of nods. And the other point to make is that what we're doing is we're comparing fields that might have been in contrasting management for a long time. So those best performing permanent pasture fields have probably been permanent pasture for a long time. They've built lots of carbon. So this doesn't really give us an insight into how long it might take to get there. It might take 100 years to achieve this potential, which is obviously important to know for entering carbon markets or whatever. So we need to understand the rate or the dynamics of that carbon capture. But this second paragraph here is really important, I think, for the work we're continuing to do. And Luke, can you just put your hand up? Luke has just started with me. So Luke's a placement student from Lancaster University, doing an environmental science degree there. And he's going to be with us for 6 to 9 months. And one of the things he's going to be doing is exploring what are the reasons between the individual fields that explain this potential. And I think that's going to be fascinating. So, we're talking about rates now. So that gives us the potential uplift, and we've kind of used this approach in the water modelling that we'll move on to. But then we need to know how fast you're going to capture that carbon. And that's where we have to use models. And again, the point to make, I'm not going to go into all the detail of this, but you can use these models in 2 ways. You can just model it from first principles and use parameters from the literature, or you can use our real data from the cluster, which is what I've done, to parameterize this model. So this model, if you like, has been tailored to the cluster. So it gives us a bit more confidence in the outputs. This is the Rothschild model that you might be familiar with or have heard of, and it's just very simply, it's balancing how much carbon you're putting in every year with how much carbon you're losing every year. So the amount of carbon that you're putting in is to do with the plant inputs and the productivity and how much carbon is going in from the roots. The rate of breakdown is to do with those different carbon pools that Stefan was talking about. It's just to do with the microbial activity, it's to do with the climate, the moisture, the temperature. So what the model does is it just keeps track of all those things and keeps track of the balance. How much is going in, how much is coming out. And again, we use the data from the cluster to provide the inputs for that and effectively run it. And I've got a nice picture of a legume lay on the right there, and the model also includes grassland and herbal lays or annual crops, so we can look at those different effects. And this is the kind of output you get. So if you remember, going from arable to grasslands, you're getting about a 50 tonne to 100 tonne uplift, and then this is running it for 30 years, and this is where you get to based on the model. So we're kind of going more or less to the right target where we want to get to, and we're here after 30 years, you're here after 10 years. So it's about a tonne and a bit over a tonne per year initially of extra carbon if you go arable reversion to improved grassland. And then the herbal lays, obviously during the arable phase you're losing carbon, and in the improved grass lay phase you're building carbon, but overall you're increasing but at a slower rate than the grass. So the point is that we can use this. We're starting with the empirical data set, we're starting with the baselining, but then we're plugging that into the model to give us an estimate of where we might be in 30 years' time, which is what Emily has used for her flood model, which I'm about to move on to before I introduce you to the land management scenarios that we have explored. And I think this is a starting point. I think within a cluster context, again, we were talking about trees, there's agroforestry, the silvopasture, there's lots of different, and Tim had that nice slide with all the different interventions. We've just looked at these three so far, which are arable reversion to improve grassland at the bottom. So they tend to continue to have high productivity, high carbon inputs, but those carbon inputs cycle more quickly because they tend to decompose more quickly. Arable to a herbal lay was that orange line where you get increasing carbon, then you're losing it through the arable phase. And in our particular scenario, we did 4 years annual cropping, 4 years lays. We can play around with that, we can adjust that. And then the top one there, and this is the first time really that we've mentioned floodplain meadows, which is where we took the extra soil carbon measurements we did in the floodplain models and used them in the same approach, the same methodology. And again, that's going from what we looked at was restoring floodplain meadows in fields that were arable. What we haven't looked at is grassland restoration, where we're going from improved grassland to floodplain meadows, but again, we can look at that in the future. So we've got this framework, and we've just explored these three case studies, and that really sets the scene for what Emily's going to talk about, and we're going to talk about in the rest of the day. But are there any questions up to now about any of that? Yes?
Would you consider more scrubby, woody alternatives, or is it, are you definitely sticking with grass?
No, I think, I think what we're doing here is we're building an evidence base, and we're building an analytical framework for asking what-if questions. So I think what I'd be really interested in terms of the future of the cluster is scenarios, looking at different scenarios, and then saying, well, what evidence have we got? What models or what data have we got to say, at a cluster level, how would that scenario impact overall soil carbon, biodiversity, flood management? So specifically in this project, no, but we could and should. So we've got to start somewhere, I think. We may spill over into the discussion a bit, but we'll see. Yeah.
Do you know, have you got any idea how restoration to dry species-rich grassland compares to floodplains or improved grassland?
Yeah, okay.
Can you repeat the question?
Is there any information on how restoration of dry grasslands, calcareous grasslands, I guess, compares with floodplain meadows? No, and that's a good point to highlight that, and you need to bear this in mind as we look at the results, that we haven't really Rothsea doesn't do waterlogged soils. So it's been designed for aerobic soils, aerobic restoration, and there's lots of processes that happen in waterlogged soils that we're not currently capturing. So we can't do that yet, but we should be. And I think the way into doing that would be to do a dedicated sampling across the grassland habitats to start that process. But yeah, it's a really good question. It's a hard question, actually.
It would be fair to say that we do have the data, we just haven't analysed it, because we've got the calcareous grasslands in that data set. But next week.
Lydia.
Yeah, another quick one. So your improved grassland, first of all, what species are in there? Is that Alolian grass?
Yeah, that's my assumption.
Okay.
Yeah.
And secondly, do you maintain a particular fertility?
So these are the questions that I'm hoping Luke is going to explore.
Okay, sorry.
So in terms of grazing regimes, management of those swards, diversity of those swards, inputs, pH. So I want to go back through all the samples and look at pH, because we know that's important. So there's all these subtleties that we don't know about, which will explain all that variation. And we need to,
You said you use the empirical data to generate the model to then predict how much you might have in 30 years. Did you keep any data back then to verify that model, or how?
Good question. So
Rossi has been validated.
yes, you could. So the way I've done it is just run the model for the case study fields that we'll hear about. But yes, you could do that. Yes, you can do it. I haven't done it, but you can do it. Yeah, that's right. No, good question. And at some point I'll need to write this up, and I would need to do that for But Rothsea itself is very well parameterised and a really robust model, but it needs to be parameterised. So it was originally built on the long-term experiments at Rothamsted, which are a heavy clay, loam soil. So you need to parameterise it for your individual soil type. Percentage clay, for example, is a parameter in the model. Yes.
The top one, the meadow restoration. What are the low inputs that you're putting in? Seed or actual?
I may have written that to differentiate between high inputs, improved grassland. I'm not an expert on floodplain restoration. There are experts in the room. But my understanding is you want to keep it in low fertility. Fertility will be your enemy. High NP, so you want to be reducing.
Generally zero input unless they've always been maintained with a small amount of organic manure and then you can keep doing that. But generally very, very low inputs.
So
without wanting to digress, the floodplains of the Evenlode and Windrush do receive some input every time it floods in terms of phosphate and nitrate. You know what.
So I think one of the things we'll move on to in the discussion is this issue of soil fertility. So to build carbon, you need to have some plant nutrition. The plants need something to grow to capture that carbon. So you need nutrients in the system. But we all know that fertility can be the enemy of diversity. So there might be a balancing act to strike there. Okay, shall I hand over to... This says 12:30. Should I have spoken to another
No, I think the timing's wrong.
Yeah, good. I can fill for another 40 minutes, but no one would thank me for it.
Lovely, thanks, Jon. So hi, I'm Emily. I work for AtkinsRéalis. I'm an environmental scientist, and I'm really interested in how managing the landscape can deliver lots of multiple benefits, and how we can work with nature to deliver those multiple benefits. I'm particularly interested in soils and also management, and so we've developed an NEIRF studio tool, which I'm going to talk through today, and we've modelled that to look at the benefits for flood management in catchments, and then also talk through how we've adapted some of that modelling as part of that studio tool to start to build in the hydrological element of how much water soils can store, so we can tie together the carbon and the water benefits of soil and soil management. So just quickly, what is NFM Studio? It's an auctioneering and decision support tool that was designed co-designed with the Environment Agency to sort of help provide a proportional evidence base for the implementation of natural flood management measures, to sort of start to think about how much water can these types of measures store in the landscape. And NFM Studio sort of splits NFM into three broad categories. Firstly, sort of the land use change measures, and within this category we think of sort of three sort of scenarios, a sort of successional scenario, arable to grassland, which we'll be talking about a lot, Jon's been talking about, a woodland creation scenario, and a soil restoration scenario. And this sort of category of NFM is what we've been sort of focusing on as part of this project, and sort of the methodology applied in calculating those volumetric reductions in runoff is part of the modelling that we've been carrying forward in looking at the water holding capacity of the soils. But just also to point out that Natural Flood Management Studio also does consider flow pathway measures, so where can you store water along flow pathways, implementing flow pathway bunds, and also in-channel and floodplain reconnection measures, so storing water in the floodplains and slowing the progression of flood peaks through the catchment as well. Just to quickly touch on where it's been used, I mentioned it was co-developed with the Environment Agency, and it was run regionally across Devon and Cornwall, so that's why a huge part of the country there is sort of ticked off there. And we've run it for now over 260 catchments across the country, and every time we work with a new catchment, we're working with different partners, aim to sort of develop and evolve the model to sort of build in and make it different elements and make it more locally applicable and hopefully more robust. So for example, working with the Environment Agency in the Calder catchment in North Yorkshire, looking at how we could build in peatland restoration measures into understanding how peatland functions in the hydrological system, and how restoring peatlands also influence natural flood management responses. And also the Froome catchment over Bristol, developing and integrating it with the sustainable urban drainage model outputs, so combining the benefits that can be achieved from the different types of measures, natural flood management and urban sustainable drainage, because that catchment had a particular rural upper headwaters and then quite urban lower part of the catchment. But today we're in Evenlode, it's another one of the catchments where we've run NFM Studio. I'm sure many of you are very familiar with this catchment. Just a little map of it up there. It's predominantly arable catchment, and the NFM Studio results are sort of, although it's run for the field scale, so you can map up the outputs spatially, we've summed up all the outputs from across the whole catchment, and that's what's in those bubbles in the bottom left there. And NFM Studio is suggesting there that the land management scenario, so changing the land use change type measures, have the largest volumetric benefit. This is not massively surprising. We're implementing these types of measures across a much bigger area, and of the scenarios applied as picking out woodland creation as the highest volumetric reductions in runoff. And again, this is not hugely surprising. Thinking about not only the changes to the soil that having woodland has, but also the interception potential that the trees and canopy cover provides. And then also we've got the volumetric benefits from the flow pathway scenarios, and also the in-channel and floodplain reconnection type measures as well. And it's worth pointing out that these volumes are summed across the whole catchment, so this is if you were to do these types of measures in every field across the catchment. And this is very ambitious. It's not perhaps very realistic, and we won't necessarily see that, but it's very helpful to look at it as a whole at a much larger catchment scale, to think about the potential that natural flood management might have at reducing downstream flood peak if you really did an all-in type scenario. But because Natural Flood Management Studio also considers it at the field scale. When you look at the spatial outputs, you can really target measures to fields where it's showing the highest uplift potentials, the fields that have the greatest volumetric potential, and we can pick out those and prioritise where measures can be implemented there. So the hydrograph on the right there is showing the sort of baseline flood peak, and then the yellow line there is showing that if all those volumes were captured, if you're implementing flood management in every field in the catchment, what impact that might have on the flood peak. So we take all those volumes and take them off the hydrograph, and it's showing a roughly 33 to 38% decrease in flood peak, and that's shown by that yellow line. And then the hash area is representing the volume that is held in the catchment from these types of natural flood management measures. But obviously today we're here to talk about soils in particular, so I've sort of repeated that hydrograph bit of analysis, but just looking at the outputs from the soil restoration land use scenario. So if you ignore for the time being the flow pathways and in-channel measures, what is it just that the soils can store? And summing that all up across the whole catchment, implementing everything everywhere, we're looking at about a 21% decrease in flood peak. And this is also just this is the sort of the starting point of the soil carbon and water resilience project. This is using up to this point using open source soils data, deriving soil texture and soil bulk density information from sort of parent material open source data, and so therefore it is quite coarse resolution across the catchment, so we don't pick up any of that variability that Jon's been talking about, that we see not only in the field scale, but within different soil types, but also within different land management practices and all the other environmental variables that results in different soil textures. So this 21% decrease of flood peak is using this really coarse data set, and also it's making quite broad assumptions in the reductions in bulk density that are being applied in the modelling. So by saying soil health and soil restoration measures, we've applied a percentage reduction in the flood peak in the bulk density to account for measures, for example, like aeration and reducing compaction. So some broad assumptions that we made up to this point, so really highlighting why working with Rothamsted and the farm cluster and using the empirical data set can be really helpful to build up and increase the sort of confidence in the modelling approach for the sort of soil natural flood management benefits. And as Jon sort of showed a breakdown of the Roth-C model, this is a quick visualisation of the soil water modelling approach. Its official name is the daily-based Morgan-Morgan-Finney model, and there is a link to the paper there. But essentially it's a very relatively simple model that treats the soils a bit like a bucket. There's parameters on the size of that bucket, how much water can be held within the soil, and it's all around the soil texture and soil porosity information that we feed into it, and therefore the soil information from the soil survey data has been really helpful to sort of supersede that really coarse resolution open source data set. Also, how much water is held naturally in the soil. So this, before you apply rainfall to the model, how much water is currently held in the soil, and we determine this to be field capacity, which is how much water is held under gravity to the soils. So if you were to dunk a sponge in a bucket of water and lift it up, and water would pour from the sponge, eventually water would stop pouring, and that's the point where we reach field capacity. And if you were to squeeze it, it still contains quite a lot of water, but it's not falling out the bottom of your sponge, and so that's field capacity, and that's the initial water content of the soil in the modelling approach. And there's also inputs in terms of rainfall, so we apply rainfall to the soil model, and that is intercepted by the different vegetation types that are on the soil surface. And then there are also losses from the model in terms of infiltration to depth, and that is determined by the sort of speed at which water can travel through the soil and the ability for the bedrock and parent material to sort of also allow for infiltration. And so the sort of modelling outputs which we're quite interested in, I suppose, is the ability for the soil to accept more water, and that is the soil water storage capacity. And also then the excessive amount of rainfall is the amount that runs off the soil surface, and that's our total runoff. And so when we're thinking about natural flood management, it's this sort of runoff reduction potentials that we're sort of talking about. And here today we're talking a lot more about the soil water storage capacities, how much water can we hold in that soil for longer, and sort of delaying the progression of intense rainfall straight through the catchment. And as we're talking about any modelling approach, just worth touching on some of the limitations, and I've sort of mentioned some of those in terms of the fact that the parent material model is sort of quite a coarse resolution, so improving it with higher variability and locally specific data set has been really important. And some of the limitations on also thinking about how much water can be held in the soil, so that we've determined that the porosity of the soil is also equal to the saturation volume, so we assume that these soils can go up to saturation. And so these graphs, as we've already seen, the soil organic carbon one Jon talked through earlier, just sets the seed for the reason we had this soil carbon and water resilience project. Being able to use the empirical soil texture data across the whole cluster, that really sort of picks up the different variations in the soil types, the soil, the land covers, and also different farm types, and to be able to start to map together the soil organic carbon with the soil water capacities, and really tying together those multiple benefits that soils can provide. And I really whizzed through those. Happy to take some questions, and that was a quick introduction to the natural food management tool, and how we've then started to adapt it for looking at the water benefits. Yeah.
I love the fact we actually cut a load of slides out because we were so worried.
That's probably my fault. Let's go to
I'm Brian Barrett, Level Grail Project Manager on Climate Change Adaptation. On one of your first hydrographs, when you showed the reduction in the peak, it was quite a vertical jump to that peak. What was the reasoning for that with the interventions in the fields?
Sorry, go back through maybe.
Yeah, that
this one.
Yeah.
So there's, as with most modelling, I suppose, there's been quite some broad assumptions again made in how you take the volumes that the modelling is showing that can be reduced in terms of reduction in runoff and stored in the flow pathways, and how we implement that volume into the hydrograph. So the hydrograph showing the flow there, so there's assumptions based in how the volumes are then converted into the flow. And so how that's been applied in the hydrograph is set sort of stepwise, so the different NFM typologies, the volumes have been summed up separately and then applied in a slightly different manner to the hydrograph, so the land use change volumes are applied sort of uniformly across the hydrograph to sort of show a reduction in runoff being generated by the catchment as a whole. And then the flow pathways are taken off like a nick from the front of the hydrograph, which I suppose just explains that sort of sharp rising limb there, to represent the fact that these flow pathway storage bunds are sort of filling up as the event starts, and then once they become full, the water then continues down to the catchment. And then in channel measures also apply a bit of a smoothing to the hydrograph as well, to sort of show that sort of delaying and sort of smoothing of the hydrograph, that you'd see those kind of you'd see with those kind of measure types. But no, yeah, good question. lots of assumptions with modelling.
Hi, I'm from Devon. So you said you covered 260 catchments in Devon and Cornwall. Is that data available?
Yes, it's on an ArcGIS online web link. You can definitely make sure that gets sent round. Yeah, it was working in the Environment Agency, Tom Dorgan in the Devon and Cornwall region. So yeah, that's all open source, which has been the sort of main ethos in running a lot of the studio tools that we've developed within Atkins, to make sure that it's using open source data sets so that they can be, outputs can be shared and hopefully helpful to the partners and things and people who are looking to implement measures.
It's worth just mentioning that the Evenlode data set is, we find a link on cotswoldfarmers.org through the landscape recovery section, but also I think on the ECP website as well, the Catchment Partnership website. So there's a whole heap of other data on that NFM studio, which is really valuable.
Yeah, thanks Emily for that. I was just wondering, obviously having some understanding of the modelling process and so on, what the advantage has been having this amazing data set that you have, and how to a certain extent it changes the outcomes, if at all, or the other piece of the thing, if you wanted to do this somewhere else, can you rely on those sorts of broader data sets? I think there's a really important question there for, and we're talking about Devon and Cornwall and other communities at risk from flooding, is how much data do we actually need, and how important is it to go to this level of detail? I don't know if you have just a general reflection on that might help.
Yeah, no, thanks. Definitely, it's been a really helpful process to go through. When we've run the tool up to this kind of point, and so for Devon and Cornwall and for the Evenlode, as like in the outputs shown here, it's all using open source data sets. The soil, getting that soil information has obviously been a bit trickier, and so we've derived a lot of the soil in the inputs to the soil modelling from open source soil data sets, which are quite coarse resolution, so you don't pick up the variations in different soil types as much. So I think from the baseline you don't get a true representation of what the soils are doing, and then also thinking about the uplifts, applying the scenarios, particularly with the soil restoration scenario. By working with the Ross seed model and the outputs shown there, we can really tie it against reflective bulk density reductions rather than just from the literature that we've found. So we can really make it applicable to both locally, I suppose here, but also tying bulk density reductions that are going to apply them into the model, which is much more specific. So we're looking at scenarios that are much more realistic, I suppose, and more locally applicable. And definitely interested in thinking how we then tie that in for the areas that we don't always have survey data. So like having soil survey data is really helpful for running any of these kind of modelling tools, being based on really local and validated kind of, I suppose, against specific soil survey types. Yeah, a rambling one.
So recently, both here and in the US, we've seen the weather gods using a sort of double tap approach, where the first storm comes on and soaks everything, and the second one comes on and floods you.
Mm-hmm.
How does this deal with the second storm better?
I suppose in terms of the modelling that we've done, hasn't thought about antecedent conditions in huge, that adds a whole other level of complexity. The model's set up that the sort of initial water content is based around that sort of fill capacity and tying it in there. So it does it's modelling that the fact that the soils are holding water but not really saturated. But it is showing that particularly the land management change scenarios are showing really large volumetric reductions in runoff. So it's suggesting that even if you were to do those types of measures, you could start to build up more space in the soils so that at some point they might be full and they might be fuller depending on what's happened previously, but starting to think about the sort of uplift potentials that can be achieved and sort of making the soils work a little bit more as a store of water in the landscape, and recognising that natural flood management might not be the only solution, but it definitely might get you part of the way to sort of reducing flood risk downstream.
Thanks, Emily. Question at the front.
Thanks. I'm very new to the subject, so at the risk of asking a very obvious question, could you go to the last slide again?
Yeah.
It seemed to me that was quite a significant. So you didn't explicitly say what the conclusion of that slide is. Is it that water capacity, high water capacity equals high soil level carbon?
Yeah, no, and apologies for skipping over this one. I think this was meant to be a bit more of a taster slide for some of the conversations we'll have when we're introducing the project, the Soil Carbon and Water Resilience project a lot more. And we're definitely pulling out the sort of relationships between water capacity and organic carbon. But this was just to start to say that the sort of value in tying them together. And Jon, I suppose we talked about looking at the variations in the soil organic carbon and understanding what might be driving that. I suppose the same applies for the sort of water holding capacity as well. So we can start to map the baseline and understand spatially where are those fields that have the higher holding capacity, and what might be driving that. Land use change would be a big part of that, but there'll be other environmental variables, soil types and textures, and how can we sort of get that uplift in those areas where they're slower. So yeah, more to come on that one most definitely.
Alex Ward. Emily, could you take us back to the slide where you had leaky dams and bunds? So the bund slide, surely all that's happening there is as the stream is coming down, it seems to be getting narrower and narrower. So I assume that obviously must be getting deeper. Is that what it's trying to explain? I'm sort of.
Sorry, this sort of graphic was just trying to illustrate a little bit what a bund might look like type thing, and I suppose this here is sort of it's a surface flow pathway rather than a stream, and I suppose it's a sliding scale of water starting to run off the field, being channeled into sort of initially smaller flow pathways, then eventually larger flow pathways, and then into the channels and streams and main rivers. But to sort of start to think about how we can map the flow pathways across the landscape using the topography and things, and starting to think about how we can target the location of bunds to really maximise the sort of storage capacity, sort of to capture the surface runoff that's coming off fields or other sort of solutions. So yeah, not to scale drawing there.
Like for the farm walk, we could probably get an indication of what one might look like out in the field below us here. That's on right next to you.
Thank you. So I have a slightly unstructured question. It relates to the very, very low rainfall for quite long periods that we're experiencing in the east now, Cambridge and further east from that, which then gives you the potential for, even with a good soil, with a decent carbon content, you can almost have that low wettability. So you've got runoff, even though you've got a lovely soil. And so I guess the question is, have you some way in your model of linking odd, persistent drought periods with what happens afterwards?
Good question. I suppose, as I talked through the diagram of the model, it is a sort of more simplistic model, and there's not that kind of huge number of parameters, particularly around the sort of very complex relationship of the soil surface where water is intercepted and by the vegetation and starts to infiltrate. This particular model you said we've been looking at doesn't have the ability to sort of look into that in a huge amount of detail. Definitely really important part of sort of like process is how water actually gets into the soil, and that in itself is tied against lots of different processes, land cover being one, but the sort of the rooting processes, and there's huge, and the fact that when it's dry it can often repel water to the extent as well. So definitely a very complicated part of that process. But then to touch on the sort of ability for soils and to act as sort of drought resilience, I suppose, as well. This is probably something that we'll discuss later on in the discussion as well, but thinking about water, so soils as a store in the landscape, not just for intercepting when there's too much rainfall, but also sort of releasing that more slowly and having it available in the landscape when it's drier as well. And again, the soils have a role to play maybe, but aren't necessarily going to solve everything, but can definitely help retain water for longer, and act as that kind of sponge in the landscape.
Your analogy of the sponge is brilliant to explain field capacity, and ultimately the point we're trying to prove is you increase your soil carbon, reduce your belt density, increase the size of that sponge, not just to absorb your floods, but also to enable that water to stay in the soils for longer for the drought periods as well.
I think this is absolutely fantastic. I really enjoyed your presentation. I'm thinking about natural flood management from the point of being a farmer, a single farmer. I have a brook which runs across my farm, and I know there's downstream flooding. So I was thinking, how do I want to actually start on some natural flood management as soon as I can manage. And I was thinking about how to measure the effectiveness. So, so in a sense this is a bit crude, but if I think about where the brook enters my land at the upstream end, and measure the change, the sort of profile of the change in water depth if there's been rain, significant rain, and then just see how smooth that is by the time it leaves my land. I don't know whether that's at all, it's really difficult to know how to measure in an objective way.
No, fantastic question. There are probably many others in this room who can help answer that one as well. But I suppose it's, you'd expect to see natural flood management measures to sort of smooth any sort of spikes in flow and things, and sort of, attenuate it a little bit so you don't get the rapid response and water just rushing through. So you'd hopefully see that measures would retain water a little bit and slowly release it, so you'd sort of see a smoothing of any sort of hydrograph rather than something really spiky. Exactly how you do that, I think I wouldn't exactly know, definitely not a specialist in that, but no, fantastic. Perhaps we'll pick that one up later.
Thank you.
Emily's getting all the questions.
We'll be fairly honest, 40 minutes. We might move on to the next session.
Oh, we could,
because it is probably verging on answering some of the questions you're getting. But let's see where we go.
Hi, I'm Ian Simpson, Bledington Flood Group. So if you could go to the next two slides, please. So I'm just going to put it into context in the sense that I am one of the consumers of flood water. And we've benefited from NFM, so it sort of just follow on from your question. The flood groups have been working insidiously the past 4 years, and Emily's famous swimming pool analogy. Bledington's at the top left, and we have 1.2 million cubic litres of water meters of water in the village in 2020, which equates to 470 swimming pools, I believe you said. So I just wanted to highlight the role, therefore, that NFM has played in actually forwarding our scheme in terms of protecting Bledington as a village. Well aware that all you guys sitting in here are the key stakeholders, the farmers whose land and water runs through, and off. But I also wanted to highlight, and Emily, you can comment on this, the collegiate sort of effect of getting everybody to work together, and how your NFM has then spun off in terms of getting funding for us to actually progress the mitigation, flood mitigation that we need through the local authorities and the Environment Agency.
Yeah, no, it's definitely been really helpful to see how the outputs have been really helpful to start to get measures implemented. And to Tim, you probably know a bit more about how that all came about.
Yeah, we might dive into this a bit later on, but it's a really interesting one, natural flood management, in trying to deploy it at scale across the landscape. And having this conversation in Cardiff a couple of weeks ago with these guys, who pays for it? Because we'll come on to that later. But what you need is a few inspiring case studies, like you got at Bleddington, like at Cornwall, like at Bruin, which is a wonderful demonstration of that field corner bund concept. And we need the local authorities to lead those case studies so that we can prove them in the absence of huge amounts of data, seeing is believing more often than not. But then we can start to work on some of the other stakeholders in the catchment, be that Network Rail or Thames Water or further down. So we'll come on to that a bit more later perhaps. But Jim?
Thanks, Tim. Jim Elliott from 3Keel, and potentially based on what you just said, my question is for later, but I'll ask it anyway and you can decide whether to answer it. So yeah, I'm interested in how we capture the value of the NFM work that happens and get people to pay for it. So I was interested in, so obviously this is providing us with a percentage reduction in peak flow. Are we able to then convert that into what it means in terms of reduction in flood risk in particular places, like the village or a factory or whatever? What's the kind of level of certainty on the flow peak reduction in this model? Like, are you able to say, yeah, assuming that the conditions in real life were exactly as they were in the model, this is nailed on, 100% guaranteed that you'll have a 33% reduction in the flow peak? And do we have an ability to calculate the actual risks around, for example, the question before about if you've got consecutive events, that obviously drastically changes the background conditions and the assumptions that went into the original modelling. So do we have an ability to calculate that risk so that you end up with a kind of a bit more of a genuine real world view of, okay, for the village of Bleddington, this is actually the amount of kind of real flood protection that's being provided by our NFM measures.
Thank you. That's a multi-layered question there. I will do my best to answer parts of it. I guess in terms of thinking about the first bit was around properties at risk of flooding. This NFM you do has been designed to sort of provide the first step in going towards providing the evidence base for why you might implement NFM to sort of support to speed up its implementation, to provide sort of that balance. It's not a really detailed hydrological model that perhaps takes a lot more time and money to develop and evolve. But it's not just an opportunity layer, it's somewhere in between. So as the outputs from the studio tool are, it doesn't think about property level resilience, but we can take some of those outputs forward and work with colleagues who specialise in hydrological modelling and input NFM outputs into their models to sort of start to think about the output of property level resilience. Was it the middle part of the question was around the uncertainty around those peak flow reductions. Obviously, this is modelling, so if the environmental conditions were to be exact as all the many assumptions that are applied, then maybe, but the percent of the range there is also to demonstrate the fact that we've run different return periods as well. So natural management is commonly more effective at smaller return periods because the volumes that you can start to store and reduce are a bigger percentage of the total amount of water that's passing through the catchments in those smaller events. So also to reflect on the fact that there's ranges in rainfall intensity in periods, so as well as the conditions beforehand, there's also during the event there can be many different variables that start to add complexity into that, and it's definitely a starting point and showing that sort of the level of confidence to that these are good things to be doing. So definitely get started in them, I guess. So I hope that answers parts of your question, if anything.
I could probably just answer a few more of them actually. You've got Ian sat next to you. This process has been run through. The questions you've asked was actually run through for the Bledington community to try and help build a business case. The questions you ask are super pertinent. It's not easy currently to build a business case for NFM because of the certainty of things that you rightly describe. And when you describe some of these data to say an insurance company or a broker, like what I'm trying to do recently, it's that question that you're asking around trying to fit, a square peg into a round hole. The understanding that we each have of certainty and risk is completely different. It's very clear we know that what we do in the landscape has an effect on flood risk. The precise magnitude of that effect varies depending on the assumptions you make or what we all do. But if you're an insurance broker, it's what you ask is, I need to know exactly what it is. And I think how we convey risk and uncertainty to promote some of these things and help protect people like Ian and other people in the catchment from flooding is absolutely essential. So I think the question you ask, if we think about NFM rollout at a sort of policy level even, is one of the key essential things we need to talk about. I mean, the business case for Bledington, it's taken a lot of time to do. We know that, and I think that's part of the learning that you do. But if you are interested, do have a look at that case study. I personally think it's one of the best NFM business cases out there purely because of the involvement of the local community in that conversation. It hasn't been easy either. I think it's fair to say. We've had lots of difficult conversations about it, but it's how do you actually fit it into the policy framework that we have. The reality is that I don't think the policy framework is ready for this, and I think it's because of those questions that you've just described, and that's the value of sessions like today, where we're really getting under the bonnet of really detailed data that you need to improve the certainty and to give people confidence that we're not just saying, oh, just do this and everything will be fine. We do have a science base, but so thanks for your question.
So just to follow up, sorry this is Bledington centric all of a sudden, but it's a case study. Part of an NFM study that you did for us, and I'm talking today, instrumental in that and Emily as well, the financial impact, and as part of the NFM report, the NFM studio report, it calculated that the cost of flooding in Bledington on December the 20th, 2020 was £1.8 million. So that then puts into context that perhaps if we can spend £500,000 in actually mitigating against that flooding, there is that cost-reward ratio, and we're not going to go into PFC, PFRs and all the rest of it, but what it does do is support the business case. There's one point, and I know Tim will start jumping up about an agreement, NFM isn't included in the Environment Agency risk assessment. And it's something that I've got Evie and Al and people Sarah are looking at. But when we're going to be doing NFM work, which we've done a huge amount, we've spent about £150,000 of NFM work in Bledington, but not on NFM work, we input it into the Environment Agency mapping for risk, and I think it's really quite an important factor that needs to be addressed, because you've got a figure there of 1 bun per field. We've got 5 buns up there holding back X amount of water, but that isn't included in the PFR that you've been talking about, the property flood risk assessment. And that has to be, and that needs to be addressed. So, sorry.
but Joe, I'm going to go to you first.
Yeah, it was just to quickly say that quite a few of us worked on the NFM project at Broad Estate, and that had the luxury, well, quite a few groups came together to quite intensively monitor that project, and so there are some quite good data sets from the Bruin Estate and the effectiveness of NFM, and we did have data down at the properties, and it was quite intensively modelled, which I know is unrealistic and you can't do that everywhere, but you have got a really good data set in this catchment, which Izzy, I think, is able to share now. We've got the reports that can share.
That's going to be really useful, actually. If I may take the chair. Oh, and do you want to come on that?
Can I just build on that? Sorry, Evenlode Catchment Partnership. I just want to make the point, as Joe says, the amount of work that went on in the Evenlode and the instrumentation and the reporting of that was very fine-grained in order that we would all be able to learn lots of lessons and improve the models from there. Those lessons then built on to what's been able to be done in Reddington and so on and so on. I'm going to just wave a tiny flag for the role of the ECP, which is a sort of kind of invisible, the Evenlode Catchment Partnership has been something that's quite invisible in all of this. Rightly so in lots of ways, it's a partnership, it's a bringing together of people, but actually we need to keep funding things like this, because if we don't, then all these things which are policy type issues will disappear again. So we have to keep the momentum going, as with the farmer cluster, to keep the embedded social capital and knowledge going. Otherwise we're not going to have a case to make.
Ordinarily, I give a big shout out to Catchment Partnership, but have I today? No. I mentioned it once in passing, so that's big apologies from me, because actually the ECP, which Dave and Joe, many of us have been involved with from the very beginning, actually a lot of the data, everything from grassland surveys to these case studies, has all come through the ECP and the Smarter Water Catchment project. So you cannot underestimate the value of that partnership working at a catchment scale, because ultimately the farm clusters are only going to penetrate certain parts of that partnership. At risk, I think we probably will pull up short of lunch rather than go into the next slides.
Okay.
But I am going to just, if I may, just go back. No, that's the slide. It's a really interesting conversation we had in Cardiff the other day. Cardiff is where we went to the Network Rail meeting, where we looked at the cost of designing and permitting, consenting, and so on for a very direct natural flood management solution to a direct problem on the embankment of the railway line, where the scanner is undermining the embankment. So the opportunity to move the river away, reconnect the floodplain, dissipate the energy across the floodplain, actually one of those photographs I showed earlier, and take the energy away so that the embankment could be stabilised again and then the threat taken away. It's a really direct opportunity that you can model in everything else. Unfortunately, the modelling and the design work was 50% more than a rock bag or rock revetment solution that you guys could do in your sleep. And so we then got back to the drawing board a bit, and then we thought about, well, what about the other 27 places you've got Scarrow on the Network Rail line, and the other, and what's the aggregated benefit of looking at all of these in the whole, and the cost to do the direct pinch points, and then all of a sudden it starts to look more favourable in terms of business case. And then you look up catchment at slow water before it gets to your pinch point. And the other part of that conversation was around, this isn't necessarily going to stop flooding. We're not trying to work miracles here. When we get that kind of rain on saturated soils, you're not going to stop it with NFM alone necessarily. But you could be more resilient, you can stop it happening as frequently,
and your recovery can be better. So like that slide where the ballast and the line was floating in mid-air, you know, maybe next time it won't be. It might flood and you might have a day off that line, but you might not be shut for 6 weeks repairing it. And so it's not necessarily removing all risk and saying you're protected, but you know, are you reducing the frequency of that risk of damage, and your recovery time is reduced as well. So it's worth thinking in mind that we can't work miracles, and we don't know what's coming around the corner. Pete's now gone, but Pete gives a wonderfully apocalyptic talk in most meetings where we're all doomed. And I think it's worth just bearing that in mind that, you know, we don't know what's coming around the corner, but we can be better prepared. And when you look out of the window to your left and look at the landscape of really quite, okay, there's stubbles on fields at the moment, but really quite a naked landscape. If we're increasing surface roughness, we're building soil carbon, we're creating a bit of lag in that surface runoff before it hits the streams and ditches. And you have to it can only be doing good. It's not going to hurt. And the other thing which we're going to touch on after lunch is, right, if you were just going to go for natural flood management, you would be sticking up funds everywhere, you would be reconnecting every ditch, you would be flooding every field before it gets to the railway line or the community or wherever else. But we're not in that ideal world where we can just look at NFM. We've also got to look at carbon building, we've got to look at biodiversity, but we've also got to feed ourselves as well. So it's optimising those different outcomes, and we've got to think about all of the different outcomes we're going after, which is why this project is so interesting, where you can go after carbon and have a natural flood management benefit, rather than just fund creation, or just floodplain reconnection, or just floodplain meadow creation. What are the gives and takes? And that's what Jon's, you know, the brain box behind all of this is what are those compromises and opportunities. I think we might pull up 20 minutes early for lunch. Lunch will be served at 1, but we might try and start promptly after lunch, so that we can get on the farm tour sooner, or you can get home sooner. Thanks very much. Is it 12:30?